Now, with this similarity of samarium boron 6, which we are interested in, it turns out that samarium boron 6 has been shown to have a conducting surface state below about 4.5 Kelvin. And that's evidence that samarium boron 6 is a correlated electron topological insulator. And there have been a number of experiments that have proposed this or provided evidence for it. And in fact, theoretical arguments have been advanced that condo insulators could be topological condo insulators. So as I said, the conducting surface state below 19 Kelvin in iron silicide is reminiscent of a topological insulator and suggested to us that iron silicide could also be a candidate for a d-electron version of a topological condo insulator. So this basically motivated our experiments to explore the bulk and conducting surface state of iron silicide with magnetic field and pressure and compare the behavior of iron silicide to that of the prototypical topological condo insulator samarium boron 6. Okay, so let me say a little bit about the conducting surface state. So I showed you the data in the upper left-hand panel a moment ago. Turns out if you take and look at various crystals with different diameters, the resistivity decreases once you're in the region where the conducting surface state appears, as indicated in this figure. And this is evidence for this being a surface effect and evidence for a conducting surface state. Also, if you look at the specific heat plotted versus temperature, it passes very smoothly through the region where this metallic behavior appears, and certainly there doesn't appear to be any evidence of a phase transition in that temperature range. So we're pretty sure that one has a conducting surface state in iron silicide below 19 Kelvin, and this has also been confirmed by several other recent studies. Okay, so we wanted to look into this further, as I said, with magnetic fields and pressure. I'll come to the pressure in the end. But in the left-hand figure, this is reduced resistivity versus temperature. Again, it's similar to what I showed you for different samples. In this case, it's the same sample that's been thinned. And so you see the drop in the resistivity. And you also see the separation between the normal state of behavior and the contribution from the surface state, suggesting that the onset of the surface state could be at a higher temperature than 19 Kelvin, maybe of the order of 35 Kelvin. The center figure shows the strong negative magnetoresistance in fields up to 9 Tesla in this field range. And again, this red dashed line is just the fit to the normal state. Well, not normal state, but anyway, the bulk resistivity. And then this is an log of R versus 1 over T plot. And again, you can see that in the semiconducting bulk state, the resistance is insensitive to magnetic field. And then the conducting surface state has this negative magnetoresistance. Now, I should say that the crystals that we're looking at grow in the 0, 1 bar 1 direction. That's also the direction of the current. The magnetic field is applied perpendicular to that axis of the crystal. Now, here are some hysteretic magnetoresistance, or this is the hysteretic magnetoresistance of the conducting surface state. Oh, this is a little complicated, so let me just try to explain it. So again, we have this configuration that I just showed you, and these measurements are made between -4 and +4 Tesla, and the rotation of the crystal is around its axis like this. That's the angle theta, and what are plotted here are these angular-dependent magnetoresistance plots. So if we just look at the left-hand one for this discussion purposes, you can see that The upper figure shows the behavior between -4 and +4 Tesla. The lower figure is between -1.5 and 1 Tesla to show the behavior in more detail, and near zero field, and also the curves are displaced from one another to show this behavior, or to make it more evident. Okay, so basically that same motif repeats for all four figures, and what you find then for the two sets of data taken at 2 Kelvin and 10 Kelvin, that's the left hand region, you find that the curves are asymmetric. You can see that in the upper panels, and then you see this very interesting hysteresis that is observed in these regions here. And the other thing to notice is that the change of the direction of the magnetoresistance loop changes when you go between 60 degrees and 90 degrees. You see right here very clearly. So what happens then for these two panels is that you have the resistance is asymmetric and hysteretic. The magnetoresistance loop changes sign between 60 and 90 degrees. The hysteresis suggests that one may have ferromagnetic order occurring in the surface state. And there are some possibilities that come to mind: Kondo breakdown on the surface, or there's an experimental and theoretical paper by Atsuka and co-workers where they've looked at some thin films, and they propose that there's a Zach phase derived from bulk band topology that's responsible for what they see. I'll come back to that in a moment. Now, if you look at the right-hand panels, then you see that the resistance at 20 and 30 Kelvin is symmetric and reversible. So this ferromagnetism and this hysteresis and this asymmetry seem to belong to some magnetic ordering that occurs in the surface state, and at higher temperatures it goes away when you go into the regular semiconducting bulk state. Okay, I hope I got through that semi-clearly. Okay, now let's see. Okay, so we did some other measurements looking at the anisotropic magnetoresistance, and so I have to try to lead you through this as well. So what we're plotting here are isothermal polar plots of the normalized angular dependent magnetoresistance at 9 Tesla. And the formula for that is that formula right there. We're looking at the resistance at angle theta minus the resistance at -14 degrees. That's kind of the reference point, divided by the resistance at -14 degrees. This is in percent. And it's at various temperatures for the iron silicide single crystal that we investigated. So if you look at this figure right here, you see that there's the angle 0 to 360 degrees, and these dashed or dotted green line, circular lines here represent the value of this angular dependent magnetoresistance, and the projection of the values of those curves are projected onto the vertical axis. Okay, so that just tells you what those curves correspond to. And so you can see then that looking at this curve for 10 Kelvin, you start out at this point and it makes kind of a butterfly-like shape. In fact, they all do in this temperature range. And so the characteristics are that if you want to think about it as a butterfly, the wingspan of the butterfly decreases as you go from 2 to 4 to 6 to 8 and to 10 degrees, 10 Kelvin. And the axis of the butterfly rotates clockwise. Okay, then we go to the next plot that shows what happens at 20, 30, and 40 Kelvin. Now the axis of the butterfly is stabilized, and the wingspan is still decreasing, and the shape is evolving from twofold symmetry to circular or isotropic type symmetry. And then at higher temperatures, 50, 60, 70, and 80, they become symmetric. So you can summarize some of that in this figure here. So this is the resistance for the wingspan of the butterfly divided by the minimum value. That's right in here. Divided by the maximum. It's just sort of trying to characterize these data. And you can see that this first decreases, as I indicated before, and then it increases and then decreases. And then if you look at these colors, they correspond to this lower temperature regime. This is in the conducting surface state with the loops, and the behavior is anisotropic. The butterfly orientations are rotating. Then in this region, we're getting into the range where the bulk properties are overtaking the surface properties. And this is stabilized, and we have the conducting surface state without the loop, and this evolving into no conducting surface state, and everything's isotropic. Now, these boundaries are not really distinct, but that's just indicating the different regions. So basically you have anisotropic hysteretic magnetoresistance in the conducting surface state. We believe, or it suggests it's ferromagnetically ordered 2D metallic state. And the similar type of behavior for the angular magnetoresistance from twofold to fourfold symmetry has been observed for samarium boron 6 by a number of researchers, and also samarium antimonide, which is a compound that behaves very similarly to iron silicide. Okay, so how am I doing in time? Okay, 5 minutes?
Yeah.
Okay, good. It took me a long time. Okay, so I'll try to go through this fairly quickly. So these are measurements under pressure, which are also quite interesting. This is not published. The previous work was recently. So here's resistance versus temperature, and you can see that the resistance decreases, and you have evidence again for the conducting surface state with this peak. So this decreases and then abruptly decreases into what appears to be a metallic region, and that's shown in more detail here. So there's a lot of data there. So basically, R versus T at various values of P, which are indicated there, show you the sudden suppression of the semiconducting bulk state at about 10 GPa pressure. And this over here just shows you log R versus 1 over T, different way of looking at the data. Again, you can see the typical thermally activated behavior that you see for pressures smaller than 10 GPa, where you're still in the conducting, still in the range where you have a semiconductor and an energy gap. It's at 10 GPa that the energy gap collapses. Okay, and that's summarized in this figure right here. This is resistance versus pressure. And so you see the resistance at 5 Kelvin, those are the red points. And then at 298 Kelvin, those are the black points. And you see this sudden drop in the resistance, indicating this closure of the energy gap. And another curious thing here is that when you release pressure, it doesn't return back to its original behavior. It stays down here in the metallic state. So, well, I mean, I hope that's real, but I mean, I'm sure it's real, but I don't know if that's an artifact or property of the material. So we need to look at that more. Okay, and so this just shows the energy gaps, delta 1 and delta 2 versus pressure. So you see delta 1 drops very rapidly at around 10 GPa. And so you have the presumably a topological condo insulator here, or possibly in this region, and then a metal here. And I won't bother to tell you what those other points mean. But another interesting thing we've done is these are measurements of the resistance versus magnetic field at around 3 Kelvin. And then the pressure now is increased from 2.6 GPa to 18.1 GPa. And so what you find then is that as you increase the pressure, this hysteresis loop, which we think is associated with the ferromagnetism, decreases in area as you move upwards. The magnetoresistance, which is negative, evolves towards being positive. And all of this changes again at this pressure of 10 GPa, where you presumably close this condo insulator energy gap. And if you look at the resistance, you can see that at the lower pressure regions, it's negative and large. When you start to approach this transition, it actually turns over and becomes positive, and that minimum moves to lower pressures. And then once you're well into the metallic state, it's positive like you might expect it to be for a metal. So I don't know, I find that to be really interesting. And then this is making connection with some other work, and this is Silke's very nice work from, where is the date here? 1997. And so you see things that are true stay true. And so anyway, she observed this hysteresis and the Hall effect. And also she observed this flattening off of the resistivity, which she and her coworkers interpreted as due to states within the interior of the material, as I understood, rather than a surface state. But they certainly saw the onset of metallic or nearly metallic behavior. And then this is the iron siliciide nanofilm I mentioned. And again, you see this hysteresis. In this case, they measured the magnetization of these thin films by using a magnetometer and also by some neutron reflectometry, and found the onset of the currents of ferromagnetism. Although this is a rather different situation. Okay, so just summary. Hysteretic behavior in the magnetoresistance occurs in the conducting surface state. We speculate surface ferromagnetic order. The symmetry of the angular magnetoresistance evolves from twofold in the conducting surface state region to isotropic in the semiconducting region at higher temperatures. There's an abrupt closure of the energy gap, collapse of the conducting surface state, and metallization at around 10 GPa. Well, I mentioned the metallic state persists upon release of the pressure, currently under investigation. And pressure suppresses the ferromagnetism and the conducting surface state, and the hysteresis loop in the negative magnetoresistance near 10 GPa, above which the magnetoresistance becomes positive. And the overall behavior is very similar to samarium boron 6, which we have looked into in another publication I didn't talk about. And many people have, just made the point that iron silicide is composed of inexpensive and readily available elements and may be more compatible with silicon-based technology. So that maybe, maybe this will have some use in the future, who knows? And I just mentioned some other collaborators on earlier work on this subject. So I just put that up as some people I didn't have a chance to mention.